For nearly 50 years, two remarkable machines have been sailing away from Earth. One of them, Voyager 1, is now the most distant object ever built by human hands. Right now, a radio signal traveling at the speed of light takes about 23.5 hours to reach it. Its twin, Voyager 2, isn't far behind at just under 20 hours. And Voyager 1 is closing in on something no human-made object has ever done before. In November of this year, it will cross a full light day from Earth. Send it a message on a Monday morning, and you won't hear back until Wednesday. Originally launched to explore the outer planets, the Voyager spacecraft completed one of the greatest planetary tours in history. But their journey didn't end there. After leaving the planets behind, they kept going on an even more ambitious bonus mission, becoming the first human-made spacecraft to cross the boundary of our sun's protective bubble and directly sample the space between the stars. And what they found was nothing like scientists expected. The plasma was denser than predicted. It was hotter than expected. High-energy particles weren't behaving the way decades of models said they should. Even the magnetic field refused to cooperate. The simple picture we'd built of where our solar system ends and interstellar space begins was wrong. So, what did we think our cosmic neighborhood looked like? The story starts with the sun. It doesn't just radiate heat and light, it's constantly blasting out a stream of charged particles called the solar wind. This wind races outward at incredible speeds, ranging from a typical 400 to a blistering 800 kilometers per second, creating a vast magnetic bubble around the solar system. This bubble is called the heliosphere. It surrounds all the planets and helps shield the solar system from much of the high-energy radiation arriving from the galaxy. Scientists believed this bubble had two main boundaries, with a wide, turbulent zone in between. The first boundary is the termination shock, where the solar wind, after its long journey, slams into the stuff between the stars, the interstellar medium, and abruptly slows down. From there, it flows into a churning transition zone called the heliosheath. And the second true boundary, much farther out at the edge of the heliosheath, is the heliopause. This is the final frontier, the line where the sun's influence finally gives out and interstellar space truly begins. For decades, models painted this as a pretty neat and tidy picture. The heliosphere was often imagined like a comet, with a rounded nose and a long trailing tail. The boundary itself was expected to be clear but not overly dramatic. To know for sure, though, we had to go there. So, in 1977, NASA launched Voyager 1 and Voyager 2. Their grand tour of the outer planets was the stuff of legends, but their bonus mission was even bolder: to reach the edge of the heliosphere and become the first things we've ever built to enter interstellar space. They were our messengers, sent on a journey that would span generations to confirm what we thought we knew. But they ended up rewriting the book instead. The first sign that our models were too simple came way sooner than anyone expected. In 2004, Voyager 1 crossed the first major boundary, the termination shock. Voyager 2 followed a few years later in 2007. And right away, the data was puzzling. One of the biggest mysteries the Voyagers were supposed to solve was the origin of anomalous cosmic rays. These are high-energy particles in the outer solar system, and the leading theory was that they were supercharged right at the termination shock. Scientists expected to see a huge spike in these particles as Voyager 1 crossed that line. But that didn't happen. The peak wasn't at the shock. Instead, the number of these particles just kept climbing as Voyager 1 flew deeper into the heliosheath beyond it. Instead of behaving like a single particle accelerator right at the termination shock, the acceleration appeared to be happening throughout the wider heliosheath, or through processes scientists still don't fully understand. This was the first major crack in the picture. It told scientists that the way our sun interacts with the galaxy was far more complex than they'd ever guessed. If the first boundary was already this strange, what would the final frontier, the heliopause itself, be like? On August 25, 2012, it happened. After a strange transition period moving through the turbulent heliosheath, Voyager 1 definitively crossed the heliopause. It had entered interstellar space. Its twin, Voyager 2, made the same crossing on November 5, 2018. Symbolically, at least, humanity had reached the stars. But the space they found wasn't the calm, empty void many expected. The first shock came from an instrument that measures plasma density. Inside the heliosphere's outer edge, the plasma is incredibly thin, with densities around 0.002 to 0.01 particles per cubic centimeter. But when Voyager 1 and 2 crossed over, the density of the interstellar plasma jumped by a factor of 20 to 50. And it wasn't just a single, steady increase. The probes detected intermittent plasma waves, like ripples in a pond, showing that the density out there isn't uniform but fluctuates. The interstellar medium appeared compressed right at our doorstep, pushing back against our bubble with surprising force, creating a far more perturbed environment than anticipated. A denser, more rippling environment was a shock. But the surprises didn't stop there. What about the temperature? Voyager 2, with its plasma science instrument still running, was able to take the temperature of this new environment. Pre-Voyager models generally predicted that the interstellar plasma just outside our bubble would be relatively cool, maybe around 7,000 to 10,000 Kelvin. Instead, Voyager 2 measured something much hotter. While there are still uncertainties in the data, analyses point to temperatures between 30,000 and 50,000 Kelvin. This discovery led to the sensational popular science nickname, the Wall of Fire. Now, let's be clear, this isn't literal fire. The plasma is so sparse that a spaceship flying through it wouldn't even heat up. But the particles themselves are superheated, far hotter than predicted. This suggests our heliosphere's journey through the galaxy creates a much more energetic interaction than scientists had accounted for. Think of it like the bow wave in front of a boat. The water isn't just pushed aside, it's churned up and energized. In the same way, our heliosphere seems to be compressing and heating the interstellar medium at the boundary. Higher density, unexpected heat, a missing source for cosmic rays. These data points didn't just add new details to the old map. They were forcing scientists to throw the map out and start over. And now, the biggest question of all was on the table. What did this mean for the actual shape of our solar system's shield? These discoveries from Voyager are rewriting our textbooks in real time. It's a powerful reminder that there are still fundamental things we don't know about our own cosmic backyard. If you find this journey to the edge of science as fascinating as I do, take a moment to subscribe and join us for more explorations into the unknown. For years, the go-to model for the heliosphere's shape was a comet, a rounded nose facing the galactic wind and a long, flowing tail stretching for billions upon billions of kilometers. It was an elegant picture. And according to the new data, it's probably wrong. The high pressure and temperature that Voyager found suggests the interstellar medium is pushing back much harder than we thought. Instead of our bubble being blown into a long, graceful tail, it seems to be getting squashed. New models, powered by data from Voyager and other missions like NASA's IBEX, have proposed some wild new shapes. One idea, still heavily debated, suggests the heliosphere is shaped less like a comet and more like a croissant, or maybe even has two distinct jets flowing downstream. Other models suggest it's more compact and symmetrical, almost like a beach ball, though even those versions have asymmetries caused by the local magnetic field. The scientific debate is fierce, and it's still not settled. While some evidence might still point to an extended tail, the idea of a simple, comet-like shape is fading. Our heliosphere might be a much more compact, crumpled structure, its shape dictated by a far more powerful galactic environment than we knew. Adding to the mystery, when Voyager 1 poked outside, it found that the interstellar magnetic field's direction wasn't dramatically different from the Sun's field inside. The lack of a major change was a huge surprise, suggesting a much more complex magnetic connection at the edge of our solar system. So, if our map was wrong, what does the new one look like? The truth is, we don't have one yet. We just have the first few shocking postcards from two lonely outposts on a frontier we're only just beginning to understand. So, did Voyager prove scientists wrong? In a way, yes. But that's exactly how science is supposed to work. The Voyager missions didn't just poke holes in a few theories. They replaced abstract models with the first ever direct measurements from inside interstellar space. They gave us messy, complicated, and beautiful reality.
And here's the part worth sitting with, because it's easy to get wrong. Voyager 1 crossed the heliopause back in 2012, and Voyager 2 followed in 2018. But neither of them has left the solar system. Not really. They've left the sun's protective bubble and entered the local interstellar medium. But the sun's gravity and things like the distant Oort cloud still reach far beyond that boundary. In the clean, schoolbook sense, our two explorers are still home. They've just stepped outside the front door. We've learned that the edge of our heliosphere isn't a simple, quiet shoreline. It's a turbulent, dynamic boundary where our sun's influence clashes with the galaxy. The heliosphere isn't a static shield. It breathes with the sun's cycles, and it's being squeezed and shaped by forces we're only now starting to measure. And the journey is far from over, even as it gets harder to keep listening. Just this past April, NASA had to power down one more of Voyager 1's instruments, its low-energy charged particles detector, just to keep the spacecraft's remaining power flowing to the others. One by one, over the years, the instruments have gone quiet to save what little energy is left. Every reading that still comes back now is borrowed time, a signal you'll never get from any other spacecraft, sent by a machine older than most of the people watching this video. There's still a debate about whether the Voyagers are in a cosmic foyer, a disturbed region still feeling the sun's distant presence, or if they're already sampling the truly pristine space between the stars. As long as their dwindling power lasts, they'll keep pushing deeper. Their legacy is a profound one. They've shown us that even our own cosmic neighborhood is filled with surprises. They answered old questions only to reveal far deeper and more fascinating ones. What else have we assumed about our place in the universe? And what will the next generation of explorers find, waiting for them in the strange new frontier that Voyager has just begun to unveil?
Nobody knew any of this was waiting out there. Not the density, not the heat, not the shape of our own front door. And somewhere out past the edge of what we can see, there's probably a lot more we haven't guessed yet either. Thanks for watching. Subscribe if you want to keep exploring the edge of what we know. I'll see you in the next one.